Good morning. Can you hear me? Thank you. So let me start. Are there questions about the last class lecture? No questions? Okay. So let me review a bit of what we were doing. We have a 1D problem on the disk, and in that case, we knew the only thing we have to do is to give data here, and you will get a solution all over this region, right? Up to say some time t. Because you have a, in the periodic case, you have periodic boundary conditions. But here now, suppose you are given data in a region and you want to solve in the whole region, right? Then we know, because this energy inequality we did, that we have a region where the solution is unique, which is more or less like this, right? You blow the surface up until you hit the characteristics here, the characteristic cones, the co-characteristics cones, and then you cannot go further because there are waves that go like it. So you have a solution here which is unique, and if you want to extend it here, you have to give some boundary conditions. And that we saw it in the following. We have say this problem with a equal to 1, so this is waves that are traveling to the left like this. And so in all this part you have a solution which is this, all right? But after this point we don't have a solution, a unique solution, because we know the solution is going to be constant along these lines. So if we want to find this solution, we have to give data here, okay? So that's what we did. We imposed some data. Here was the data. So you not only have to give data in the initial surface, but also on the boundary, okay? On the right boundary. And there is a compatibility condition if you want smooth data, namely that when you go this way in this limit and you go this limit, you should get the same u. So you put this condition, that the initial data del is the same that the boundary data at t equal to 0. If A is negative, the waves are going this way, and so you have to prescribe data here in this boundary and this boundary, of course. Okay. Now, if A changes sign in the middle, you can have regions where the wave is going out in both directions, so you don't have to give anything. Or it could be that the A changes the sign so that in both sides you have to give boundary conditions. And it can happen also that the A goes to 0 at some boundary. So you get this equation only in the boundary. And so there, the solution, say in this simple case, is constant on the boundary, but you cannot prescribe anything, right? And if you have a system, the way you do, you want to see the waves that are perpendicular in some sense to the boundary. So you take the normal to the boundary. This is a covector. So for instance, in the case we were doing, that was, say, the surface x y equal to which one? Y equal to y0, say, to 1. And so the normal was proportional to the dy, okay? So you look at the matrix A here, only you look at only the component, the second component, which is dy. And so you have to look at this matrix, right? And so at the boundary, you have to look at the metric. So this is in general A, alpha, beta, and A, this metric. Let me use the capital N for the boundary, the normal to the boundary. So you have to look at this metric and check whether there are how many positive eigenvalues are. For those, you don't have to give anything. Sorry, for negative, you don't have to give anything. And for positive, you have to give data, okay? So for the positive ones, you give. So you diagonalize this metric in the boundary, okay? And there might be zeros here, and they bring problems. And we are going to discuss a bit today the problems that appears in this case. So here we did, for instance, the wave equation, the second order wave equation. We pass it to first order, the usual way, defining this in here, a new variable for the time derivative, a new variable for the space derivative, and you get this system. You diagonalize the system, you get this here, and so you see that there is a wave that goes to the right, and it's a wave that goes to the left. Right, the U plus goes to the left, and the U minus goes to the right, and so you have to prescribe data for U minus here in this boundary, and you have to prescribe in this boundary data for the U plus, and here you have to prescribe both. Because if you look at the metrics here, the positive eigenvalues give you that you need to prescribe these two things, okay? And then we saw that in this case, for instance, one can prescribe things like this, so that the outgoing wave is bounced, say, by a mirror to the interior again, and this is this condition here. And so we have an energy estimate that was so the energy is again U square. I'm back to the one-dimensional equation because after you diagonalize the system is like this. So you you take the time derivative of the energy, you get this, go through the equation, you get this thing. And from here, you get that if you give this as a data, then you can throw away this piece and you get this inequality. So you bound the time derivative of the energy by this condition, and so you can, in fact, you can say, okay, the energy at time t minus the energy at time 0 is less or equal to A times the energy, the integral between 0 and t of g squared of t twiddle dt twiddle. Okay? Here I call it left. So you have this, that the energy depends on the energy at time equal to 0, so we can put this on the other side. The energy is less or equal to the energy at time 0 plus this term. A is positive. Plus. Right, so you get a that the solution at time t is a continuous function of the initial data and the boundary data in equal footing. But here you can do a bit better of that. Instead of throwing away this term here, we pass it to the other side, okay? And then integrate in time. So you integrate this relation in time now, but with this term going on the other side, and you get that Et plus A integral integral of in between 0 and t of u square of 0t t twiddle differential t twiddle, because this is a function of t also, right? Is less or equal than the energy at 0 plus, so let me put a everywhere. Right, so you get this inequality. So if I have to draw it, is this energy is an integral over this surface t. So we have our region t equal to 0 here. So this energy is the L2 norm of u here. So this is this part. And this part is A times the energy, the L2 norm here. Yeah. And we have also the L2 norm of the solution, because this is just this. So we can say, okay, we can write this as follows. We can say that the energy, the L2 norm of u L2 norm where in a region we are going to call what? S of t, and it's this region. The S of t region is this region here. So this, the blue one, is this region. Is bounded by the L2 norm or L2 of S of 0, which is this region here. Okay? Why? Because we add, so we have the energy, which is just the L2 norm between 0 and L of u square in t x dx plus a integral between 0 and t of u square t0 dx. Here we add with an a, say, doesn't matter, 0t u square of tl, so the other side, this side here, this side, this is this side. So this is dt, huh? dt twiddle, huh? dt twiddle, and this is less or equal to the energy times 0 plus twice here a of 0t of g. I put twice here because g is equal to u in the boundary, and I have one added this term here, so I add in the other side. So we have this inequality. And whenever we have this, we have what is called that the problem is strongly. Yeah.
I don't know the graph. If E is bounded by G, I don't understand that graph. Sorry.
If E
is bounded by G.
in E is bounded by this is the bound. So E plus this is bounded by E0 plus this. If the initial data is 0, then E plus this is bounded by G. Okay? Is it clear? Oh, here maybe this is misleading. Okay, this was misleading here. This one here is this plus this. Okay, because I have to give the data in these two pieces. This other graph is when you give zero initial data, and everything depends on the sources. Strongly. So I was saying this is called strongly well posed. Why this is called that? This is to distinguish when, imagine that A is 0, right? You go to the boundary, yeah, A is changing, and you go to the boundary, and A is 0 in this boundary, say. So A is 0 in this boundary, so then at the x equal to 0, this A of x is 0, so this is not here. So you only get this equation here without this term. This term is no longer here. Okay? And if A is 0 in this side, then this term is not here because, well, any of these terms is here. And you cannot put it just like this because you don't know the values here. So you get a problem here too. Right? So, and this is called only weakly well posed. These are when A equal to 0 is weakly well posed. What does mean? Well, in both cases, the solution is T is continuous with respect to the initial data, but at the boundaries, you don't get this continuity. What's the problem? You still can prove existence and everything, but if you go to the nonlinear case, then it's difficult. You cannot prove, you cannot go to the nonlinear case. You have to be very careful and do some special things. And the reason of that is the following. Let me go to another page. Suppose you are solving dt of u equals to ax dx of u, and a of 0, say, is 0. Okay? So when you go to the, and otherwise it's positive. So you have waves that are entering here, but when you come here, the waves goes like that, and here just goes along the boundary. Okay? Then you still can say, okay, the energy, I do my calculation, get the L2 norm of the energy at T, x dx between 0 and L is bounded by the L2 norm of the energy at 0, which is the L2 norm of the initial data. This was F, say. Plus A, the value of A at L, times, no, I'm doing just a, yeah, times the integral of G of T, d twiddle T, okay? Which is the integral, so you are given G here and F here. And that's okay. But now, say, okay, I want to have a nonlinear system, so I need to control time derivatives and space derivatives. So I want to go to some Sobolev space, HM. Okay? Without the boundaries, what we say is, okay, take a space derivative of this equation, get an equation for this, and use this the same thing here, but for the, say, space derivatives. Okay? And you can even take the time derivative, do the same, and you replace here with the equation, the time derivative initially by the equation, so you get also an HM in time and space, okay? But here you can't. You can do, say, you can do the time derivative, say, you have B is dt of u, so here you go to dt of B is equals to ax dx of B, so, and B at t equal to 0 is a times dx of f. F is the initial data. So then you have the same equation, and then you get the same inequality now for B, right? dx 0L, thus the energy is bounded by a dx of f at the initial surface, and here, since we are taking the time derivative, we have to put here the time derivative of what is a full derivative, right? dt of g dt, okay? So that will be the way. Here I am missing a square. The way you do, and you get an estimate for that. But now if you want to do the same for the space derivative, say, you have a problem, because you can do everything here, but at the boundary you don't know what is boundary omega t L. This you don't know. Okay? Why? Because we have only g of t. So we don't know what is the derivative of that. Okay? So in this case, if a is different from 0 here, you still have a chance. Why? Because you say, okay, I will use the equation, and I know that if I take a time derivative and in the boundary, so dt of u will be dt of g, right? And on the other hand, this is going to be a dx of b, right? Of u. Let me put u. Yeah, u is not b, is u. So I use the equation here, right? So I can get this, right? This will be the w, so this is 1 over a, the time derivative of g, okay? So if a is different from 0, I can handle this. and so I control all the derivatives, right? So I have a boundary condition now for the equation, and I run the same process as before. And so let me write down here. So the equation W satisfies not taking a time derivative. And this had some lower order terms, which is some constant and the energy. Doesn't matter. This is not U, is W. This adds some lower order term, that doesn't matter. That doesn't change much. But what I'm going to get here is is some estimate where I have the energy of this W at T will be bounded. Let me forget about this term. This term will create a constant, and there I will have some exponentials here, but it's really not important. I will get the initial data here for this equation, which is A dx of f square dx. So this is, let me put quotation marks, because there are some exponentials here that, of t that I'm not writing down. And then there will be here A of L times the integral between 0 and t, and here I will have a 1 over A dt of g, okay, square. Okay, so this is the way one handles. If A is different from 0, if A is 0, then I have a problem, right? Because I cannot find the boundary conditions. So I cannot create, I cannot look at the space derivatives. Okay. Another way to see that I can get the space derivative if A is, suppose A different from 0 everywhere, that in that case, once I know B, once I got the equation for B, now I know that the dx of U is 1 over A B because of the equation, right? So if I have the HM norm for B, because of this I have also the HF norm of dxu of U in a space, okay, because I control all this. So the problem is when A is 0. And thus it happens. When A is 0, you have to be very specific about the equation, and there's sometimes where you have problems, sometimes where you don't have problems, and can do a proof, a complete proof. Let me show you two examples. Yeah, I have a time to do this. Let me give you two examples. First, consider the second order wave equation. But in two space dimensions. So this we take dt phi, we define b, and we take the xi and define a vector w, and so the equation is dt of b is equals to the divergence of wi and then we have a dt of wi is equals to di of b. Okay, this is a system. So I have the matrix A from here and the identity here. So now I have to look at the boundary, right? So I take a boundary normal to the surface Ni. So I have to look at the matrix, the boundary. So I'm looking now to A, I alpha beta, this metric, and apply to some vector u beta, right? U, this vector u is b and wi. So it's a 3-component vector. So here this vector, this thing is 0 here, minus ni here, because this is the action. It takes the w, contract with the n, right? So we are doing this with the vector delta v and delta wi. So here with this is just this thing, and here we get 0 here and ni here. Okay, this is the matrix, the boundary matrix. So I have to look at the eigenvalues of that and notice that if wi, let me put the index, this index up here, so that we have the correct contraction. We can take wi equal to ni, and then these parts give you a 1. So we have so this has to be 0, and so if we take this, we have the equation minus ni times should be equals to, we are looking at the eigenvalues, so I have to equal to lambda delta b, and this other equation says that ni delta b is equals to lambda ni, right? So say you take this equal to 1, so what I have to do here is, yeah, we contract this equation with ni, and then we get from here we get that we contract this equation with ni and we get delta v is equal to lambda, right? And here we have that delta V lambda is equals to -1. I have a mistake somewhere. Yeah, here is a -2 because I'm looking at this. I don't know why I put minus here. These are two pluses. So this is a plus here, and this is a plus, right? So to this to be equal, to be consistent with this, lambda is equal to 1. So it's plus -1, right? I have two modes. Yeah, because I multiply this by lambda and I have, I put the substitute delta V by lambda here and lambda square equal to 1. So lambda square is equal to 1, so lambda is equal to plus -1. I have two modes. And then, so these are okay. This is one way is going in and one way is going out. But then I have a BI delta WI equals to MI, where M is perpendicular to N. And so in this case I have when I multiply here, this by this give me 0, and this by this give me something different from 0. So I have a delta B equals to 0. So these are modes with the lambda equal to 0, okay? So I have this I can take two vectors, for instance, if this is this, no, this is 1. This is 0. I should get another solution. No, it's okay. Yeah, I'm in 2 plus 1 dimension. So I have two solutions here and one solution here. Okay. I'm mixing it with the 3 dimension. So here these are all solutions, all the eigenvectors, and you see that this one has lambda equal to 0, right? So in principle you cannot find all the derivatives, etc. For this system there is no problem. Why there is no problem? Because this is a wave equation, and for the wave equation there is no preferred time direction. So if I have a problem, we are solving something like this. So time goes like that, right? And this is x and this is y. So this way there are energies, so there are ways of writing the system in which there is no problem. Other ways. Of writing the system. that are okay. This is actually something that we found maybe, I don't know, 10 years ago, before we have this problem. Because general relativity, for instance, is a sort of a system which is a wave equation in 3D, but for phi, instead of being a scalar, is a tensor, the metric tensor. So all this is the same for the metric in harmonic coordinates. And we have a problem. We couldn't prove well-posedness with for the initial boundary value problem for general relativity, because it was a nonlinear theory, and so you cannot go past this first energy inequality. Until we realized that we could take another time and do the thing okay. So you take some other time direction that is not perpendicular, I mean, it's not tangent to the boundary. So the idea here is you do a 3+1 decomposition of the space-time, where your time directions are not vertical like this, but are like that, and then you get rid of the problem. So this is not a problem. But there are other systems, like fluids, for instance. Right, the fluids, the variables are the density and the velocity of the fluid. And in that case, for instance, if you want to put a boundary condition that is a wall, say, so in a wall, the velocity goes tangent to the surface. So in that case, you have a zero mode, okay? So when you are treating this case, you have a zero mode. And this you cannot get rid, because there is a variable that has the time, so there is a particular time direction. And you want to take the wall in that particular, the boundary, which is a wall, in this time direction. So the wall is not moving with respect to the fluid. And there you get into troubles. And this is a real problem, because there are some sort of wave here that travels along the boundary, and they decay exponentially to the interior. So this is a real problem. So in fluids, taking these things and proving things is very difficult. It can be done, but it's difficult. You have to take in account what is going on here. Yeah, let's stop here. I'm trying to think whether there is something else I should say about the full theory. Well, what about existence and uniqueness? Well, you can modify the proof. So remember, we have a proof where you have some initial data here, and we blow this surface like this, and we find that the solution here was unique. You can modify this proof to this case, right? And there you will have to give, remember, in the other you give u equal to 0 here, and some other variable for the adjoint problem b equal to 0 here. So in this case with boundaries, you will get g equal to 0 for this, and the other boundary, when you go down, you have to give another. The positive eigenvalues when you go down become negative. So in this one that suppose it was negative, I have to give g or gh, say h equal to 0. So you contract something like that, and you have a well-defined scalar product and so on. Maybe I will go through this proof later on. So let's take a break. Are there questions? Questions? No questions? Okay. We convene at 10:15.